Okay, here's 11.8, the B and C level problems. There aren't any, but the A level problems are tricky, so I thought I'd give you some help on these. So for this first one, you have to find the probability that the point is on MQ. Now they tell you that M is the midpoint of AB and that Q is the midpoint of MB. So, I marked with M that being the midpoint, I marked AM with one tick mark, and I marked this whole segment MB with one tick mark. Then they tell us that Q is the midpoint, so I marked MQ with two tick marks here and QB with two tick marks. So, getting the big picture here, if I call this distance from M to Q X, and I call this distance is also X because Q is the midpoint. And so this distance here is 2X, so that means this distance here is 2X because M is the midpoint. So then now it becomes a little bit easier to see the probability that point M is on MQ. Well, this probability right here is X. That's the number of favorable outcomes over the total number of outcomes. The whole thing landing on AB, 2X plus X plus X. So that's X over 4X, so that's 1 over 4. All right, the next problem, your friend is calling between 3 and 4, and you go out at 2:45 for a half an hour. So from 2:45 to 3:15, half hour, and your friend's going to call somewhere between 3 and 4. So let's call this amount of time. We know it's 15 minutes, but I'll just call this X. This is our unit of time here, between 3 and 3:15. Okay, because 3:15 is halfway between 3 and 3:30 here, I'm going to call this X. And then from 3:30 to 4 p.m., I'm going to call that 2X. So really the reason I'm setting it up like that is so I have something to compare. So the probability that you miss the call, so I'm looking from 3 o'clock to 4 o'clock. The probability that I miss the call is just this X. It's represented by X here. And the probability, or excuse me, not the probability, but the time between 3 and 4, that's X plus 2X. So this would be X over 4X. You can see you add these in the denominator and you get 1 to 4. I just needed some way, the reason I called this X is because I needed some way to be able to compare chunks of time. These are 15-minute increments of time. So I could have called that one 15-minute increment, another one 15-minute increment, and here's two 15-minute increments. However you want to do it, as long as you see that it's a 1 to 4 probability that you miss the call. Okay, number 5 is this. You're given this thing, you've got a bullseye and you've got this center inner ring. And they tell you that the diameter of the outer circle is 40 centimeters. So, we just happen to know that the radius is 20 centimeters. And the diameter of the bullseye in the middle is 8 centimeters. So we know that the radius is 4 centimeters. So what I want to know is the scale factor of the bullseye to the outer circle. Okay? So the radius, the diameter of the bullseye is 8, and the diameter of the outer circle is 40. Okay, so that's a 1 to 5 ratio if I reduce that. Same thing, I could have used 4 to 20. That's also a 1 to 5 ratio. So that's just thrown in there for your interest. Okay, so the probability that the dart hits the bullseye, because we're talking area now, we know that it's whatever the scale factor is squared. Okay, we figured out the scale factor was 1 to 5, and we need to square that. So 1 squared to 5 squared, that's 1 to 25. So we have a probability of 1 to 25 that we're going to hit the bullseye with the dart. Okay, now they say suppose that you've taken 75 throws. Okay, we want to know how many to expect will go into the bullseye. Probability is always just kind of an estimate in the short term. It's in the long term that it gets really, really precise. But in the short term, with just 75 throws, we would expect to have about 3 of them go in. 1 over 25 equals X over 75. So product of the means, 25X equals product of the extremes, 75X equals 3. Okay, but if I took, a billion throws, I would be able to see that probability a little bit more clearly. It would definitely approach 1 to 25. All right, this next problem has to do with balloons. So you have a dartboard here, and the dartboard is 12 meters by 5 meters, and you've got all these balloons. You have 30 balloons, and they each have a radius of 10 centimeters. So we need to find the probability. It looks like an O. We need to find the probability of hitting a balloon with a dart. So what we're looking at is we're trying to find the area of the balloons to the area of the dartboard. So the first thing I'm going to do is find the area of the balloons. So the total area, I have 30 balloons here, and the area of each balloon is pi r squared. Now they told us that the radius is 10 centimeters, so it's going to be 30, since I have 30 balloons, times pi times 10 squared. So that's 30 times pi times 100. That's 3,000 pi centimeters squared. So that's my total area of my balloons, 3,000 pi centimeters squared. Now the area of the dartboard, it's 12 meters by 5 meters. Well, we remember that 1 meter equals 100 centimeters. So 12 meters equals 1,200 centimeters, and 5 meters equals 500 centimeters. So the total area is the base times the height. I want to do it in centimeters because my balloons were in centimeters. So I want to make sure that I get my units the same. So 1,200 centimeters times 500 centimeters is equal to 600,000 centimeters squared. Now, there's my total area of my dartboard. So I'm comparing that 3,000 pi centimeters squared, that's my area of my balloons, to 600,000 centimeters squared, that's my area of my dartboard. And I have 1,000 that I can cancel out of the numerator and the denominator, so that leaves me with 3 pi over 600, and then 3 is a factor of 6, so that leaves me with pi over 200, and then that's my exact answer right here. Pi over 200 is the exact answer, and then if I want a decimal approximation, I'm going to use 3.14 as my decimal approximation to pi over 200. That's about 0.016, so that's my probability of hitting a balloon. Okie dokie, that's the end.